Now we shall see the next result under closed sets. That is the theorem. Let G be an open subset of a metric space. Let G be an open subset of the metric space M. Then G dash is the complement of G in M. That is, M difference G is closed. We have to prove this. Conversely, if F is closed subset of M, then its complement, that is M minus F, is open in M. We have to prove this. That is, the complement of an open set is an open closed, and the complement of closed set is open. We have to prove this. Let us first suppose that G is open. Let us assume that G, which is a subset of metric space M, is open in. Now, if we take a general element in G, then we are going to use the definition of open sets. If X is element of G, then by definition of open set, there exists an open ball, say B, there is nothing but the center at X and radius is R, which lies entirely in G. Hence the open ball B, whose center is at X and radius is R, contains no points of G dash. See, what is the relation between G and G dash? This is the metric space M. Suppose this is G and this is the complement of G. So now we assume that X is element of G and G is open. So there exists at least one open ball whose center is at X, completely inside what? G. This one. Because of this is the definition of open set. So definitely this open ball contains totally disconnected from what? G dash. So this open ball will not contain any point of G dash. That is clear. That is what is written. Hence B, there is nothing but this open ball contains no point of G dash. Thus no point in G, sorry. Hence X cannot be a limit point of G. So what is that by a theorem? So what is that theorem states is, so just now we already discussed many times, and suppose E is a subset of a metric space M, then X is a limit point if and only if every open ball V contains, every open ball contains at least one point of E. So this is the definition, sorry, this is a theorem we already used many times. So here what happens is, we found at least one open ball which contains no point of G dash. Okay, so it contains no point of G dash. So by using this theorem, so this condition is not satisfied. What is this condition? This condition is not satisfied. This condition is necessary as well as sufficient. This condition is not satisfied. That is, every open ball about X should contain at least one point of G. Then only that point X is the limit point of G dash. But here we found one open ball which does not contain any point of G dash. So therefore by this theorem, X cannot be the limit point of G dash. So X cannot be the limit point of G dash, and hence, see, we took any general element, and that general element is not a limit point of G dash. So every element of G will not be a limit point of G dash. That is what we are going to conclude. Hence no point of G is a limit point of G dash. And so all the limit points of G dash is inside G dash itself. That is the meaning. So G dash contains all its limit points. If a set contains all its limit points, then the set is closed. Hence, G dash is a closed subset of M. This is what we have to prove. So what we have proved is, and the other thing also is to be proved. If F is closed, its complement is open. It's also very simple. Now, so that is what we have to prove. So we have taken that G is an open set, then we proved that G dash, the complement of G in M, is closed. Now we are going to take on closed set in F. Now let F be a closed set in M. Now we have F is a closed set. Suppose this is F and this is the complement is F dash. There is no intersection between them. So okay. Now we are going to take, if suppose Y is element of, so our claim is the complement, that is F dash must be open. We have to prove it. We have to prove that F dash is open. Let F be a closed set. We are going to take one element in F dash. So that is Y. We are going to take one element in F dash. If F, then there must be an open ball. Say open ball with center at Y and radius R, which contains no element of F. No elements of F. See, so definitely there will be an open ball with center at Y that is containing no point of F. If suppose this is not happening, what will happen is, what is the contrary of this? Every open ball about Y will contain at least one point of F. Then by this theorem, so what you can tell, Y is the limit point of F. But if Y is the limit point of F, where y is belonging to the complement of f. So how can we tell that f is a closed set? Already we assume that f is a closed set. What is the meaning? All the limit points is inside the set f itself. But here we are getting, if we assume that this is not true, then this y is a limit point that is lying outside f. So again we are getting a contradiction. So that's what. If y is element of f dash, then there exists an open ball which contains no element of f, that is completely inside. So suppose this is not happening, for otherwise y would be a limit point of f, that is by this theorem, then y would be a limit point of f, which means y is element of f. If y happens to be the limit point, then y must be belonging to f. Why? Because f is closed. But we assume that y is element of f dash. How is it possible? Again we are getting a contradiction. So we are getting a contradiction. So which means that y belongs to f. This contradicts that assumption that y is belonging to f dash. Thus, if you take any general element of f dash, there exists at least one open ball which lies inside, completely inside. This is the definition of open set of f dash. So f dash is an open set. Thus, for every y in f dash, there is an open ball, say B of y colon r, lying entirely in f dash. Thus, this is the by definition of open sets. Thus, f dash is an open set. This completes the proof of this theorem. So we have to learn the definitions of theorems very well, so that you can understand the other theorems very well. So you can't skip any theorems. Now, using this theorem, we can prove the previous theorems. That hints I can give you. Notes. Suppose I take two closed sets. Suppose f1 and f2 are closed sets. Then, by the previous theorem, the complement of f1, that is f1 dash and f2 dash, are open sets by the previous theorem. Okay. So, if there are two open sets, then the intersection of two open sets is also open. This is by a theorem in open sets. You can see intersection of finite intersection of open sets is open. You can see that. So this is also open. Now, therefore, f1 dash intersection f2, this is by in set theory and its operations, you have studied this result. f1 dash, the intersection F2 dash is nothing but F1 union F2 whole dash is open. Just now we proved that this is open. Actually this is same as this. So therefore F1 union F2 the whole complement is open. Therefore by the same theorem the complement of this set is closed. So what we proved, if F1 F2 are closed sets, then its finite number of union is also what? Closed. Same way we can prove that intersection of two closed sets is also closed by using the same method. And intersection of family of closed sets you can take it, and that can be proved. So you can make a note of this hint. But anyway, in examination you can prove by any way. That's as per the wish of the student. So let's just give the hint so that this previous theorem is useful in solving this theorem. Now the next theorem is let there be two metric spaces M1 and M2, two metric spaces, and let f be a function from M1 to M2, then f is continuous on M1 if and only if the inverse image of f f is continuous on F1 only if the inverse image of f is a closed subset of M1, whenever f is closed in M2. So already we proved the same like this theorem for a continuous function in terms of open sets. So that one I am going to recall now. So now suppose this is the metric space M1 and this is the metric space M2, the metric row 2, this is the metric row 1, and f is a function from M1 to M2. So now what we have to prove is if we take one closed set here in M2, the inverse image of this, that is the inverse image will be somewhere here. This is inverse image of this closed set. This is closed set. Suppose the inverse image of the closed set which is in M1, this is also closed. This is if and only statement. We have to prove this is both necessary and sufficient condition for a function to be continuous. This happens, then the function is continuous. Same like this we proved for open sets. If you take like this an open set, the inverse image of open set under f is also open. Then if this is true for any open set in M2, then the function is continuous. Same like this we are going to prove it for closed sets, but the proof is very much similar. Very important thing is we are going to use this complement theorem, this one. If G is open, the complement is closed. If F is closed, the complement is open. Okay, like this. So that theorem we are going to use it here also and prove this theorem. This is both necessary and sufficient conditions you have to prove it. First we are going to prove the necessary part. Suppose first that f is continuous. So we are going to assume that suppose that f is continuous on m1. That is continuous at every point on m1. That is the meaning of this, continuous on m1. And let us assume that if we are going to assume that if suppose we take a closed set in m2 is closed in m2, then by this theorem, you can give the number for this theorem. So what is the complement of this theorem? I'm going to refer that theorem again. Then its complement f dash is open in same m2, right here. That theorem is, I just now showed you, or you have to write that number, or you have to cite that number, or refer to that theorem. If f is closed in m2, we are talking about m2 only. The complement, what is this complement? How is the complement looks like? So its complement somewhere, okay, this is f. What is f dash? So this space is f dash. So now we are going to deal with that f dash and complete the theorem, because already we proved the same like this theorem for closed set, open sets. You can see the topic open sets. So f dash is open in m2. So which implies the inverse image of this open set is open in m1 by a theorem. What is the theorem says is the same thing here, na? It looks same like this, but in place of closed set it will be open set, that's all. So that theorem I am going to refer here. Already we proved that one. So that theorem we are going to cite it. Very careful you have to be. Simply you should not write like theorem. That theorem statement you can give some number and explain it at the bottom of the page. So f inverse of f dash is open in m1. That is already proved. I am utilizing that theorem result. This implication is taken from that theorem. Okay. But m2, the space m2 can be written as f union f dash. That is known to that is a very simple thing. The union of a set and its complement will become the entire m2. Therefore, so what is f inverse of f union f dash? We studied in the first chapter under functions. Inverse function f inverse of a union b is equal to f inverse of a union f inverse of b. So f inverse of f union f inverse of f dash. That is, so what is this actually? m2. So f inverse of m2 equals to f inverse of f union f inverse of f dash. Okay. So but what is f inverse of m2? Because this function, this is the thing that the function is onto. So f inverse of m2 is nothing but m1. I'll get the full domain. So this is nothing but f inverse of f union f inverse of f dash. So what does this implies is this m1 is like this. This is f inverse of f, and this is f inverse of f dash. There exists no intersection. If intersection is there, then that will fall in both f and f dash. But f and f dash are what? Mutually disjoint. So m1 is written like this. So m1 is f inverse of f union. That is what we got this result. So this is m1. Hence, what do we get from this final equation is this f inverse of f is the complement of is a complement must but relative to m1 of f inverse of f dash, because the union of these two is m1, and so we say that this is the complement of this with relative to the space m1. Hence f inverse of f dash is not hence, since. So why f inverse of f dash is open? Because f dash is already we proved it. F dash of f dash is open in M1. Already proved it. Since f dash is open in M1, and hence this implies that the complement of this, that is f inverse of f, is closed in M1. This is by the theorem. Which theorem? The previous theorem, now the complement theorem, that one I am using it. So f inverse of f is closed in M1 because these two are complement to each other. If this is open, this must be closed. So what we proved is, we prove the necessary part, that is, we assume that f is continuous, then whenever f is closed, we prove that f inverse is also, f inverse of f is also closed. So we prove the necessary part. Hence the necessary part. Now we are going to prove the sufficient part. Okay, sufficient part. So now what we are going to assume is, now under sufficient part, let us assume that whenever f is closed in M2, f inverse of f is also closed in M2. We need to prove that f is continuous on M1. The same, this result we are going to use, that open sets, no? Yes. Here. The theorem from open sets we are going to use it. So the sufficient part we are going to prove it now. So what we are going to assume is, if f is, whatever set f is closed in M2, f inverse of f is also closed in M2. So we need to prove that f is continuous. Now we are going to use one theorem that I will explain at the same. Thus previously, then open sets we have used that result. We have proved that result. Now see that theorem I got. a function f is continuous, function f is continuous on M1 if and only if inverse image of every open set is open whenever G is open in this the result we are going to use it now. We are going to use open theorem, open sets results in here in the sufficient form. Now, so this is what we consider. This is M1 and M2. And now what we have proved is whatever, if you take any closed set here, the inverse image, this is inverse image of F, the inverse image of F. This is closed. What we assumed that the inverse image of F with this set is also closed in M1. This is closed in M2. So this is assumed. Now what we are going to do is, so this is assumed. So now F is closed in M2. This is assumed. This implies that this is by a theorem. Which theorem? Just that the complement theorem. Na? F is closed in M2 implies the complement F dash. This one. Other than F. This is F dash. So F dash is open in what M sorry, little bit changes you have to make, little bit, just me. We have to assume that the other way. So little bit. So I am going to make use of this theorem, sorry. So now again I will consider from M1 and this is M2. Now what we are going to prove is, we are going to prove that the function is continuous. That is what is in sufficient part. Now we are going to take one open set, sorry. This is the open set G. G is open. We are going to assume that G is open in M2 and we are going to prove that the inverse image of this open set under F, this is F inverse of G. We are going to prove that this inverse image of G is open. We are going to prove it. The inverse image of this this one. We have to prove that this is, we have to prove it. So if you prove this one by using this theorem, because this is a necessary and sufficient condition, therefore if this is true, then what you can come to the conclusion? F is continuous. That is what to be proved in the sufficient part of this theorem. Okay, now this is the concept. Now suppose G is open in the set M2, this implies that the complement G dash is closed in M2 by that theorem, the complement theorem. You have to cite that theorem. Okay. Now G dash is closed in M2 implies the inverse image of any closed set is closed in M2. Assumption in the sufficient part. Because in sufficient part we assumed that whenever there exists a closed set in M2, the inverse image of that closed set is also closed in M1. So this is by that assumption in sufficient part. Now here this is nothing but G dash. Now the same concept being used in the necessary part here. See here, yes, the same thing we are going to use it here. So now m2 equal to, now m2 equals to g union g dash. Therefore, what is f inverse of m2? It is same as f inverse of g union g dash. This is nothing but f inverse of g union f inverse of g dash, but this is nothing but what? Same like the necessary part we proved like this for closed sets, open sets. So, therefore, f inverse of g, sorry here g dash, f inverse of g dash is the complement relative to m1, complement of what? F inverse of g. But f inverse of g dash is what? Closed. Therefore, by the same that complement theorem, whatever I write theorem, you have to write that side, that theorem only. See here the complement theorem. This implies that this is closed. Since this is a complement of this, therefore f inverse of g is what? Open. Because this is closed in m1. So the complement of that, this f inverse of g is open in m1. And this implies that f is continuous on m1. This is also by the theorem, but this time it is this one. Just now I explained this one. Using this theorem, because this this part is assumed, this we proved it. So if this is satisfied, then f is continuous. So by that theorem. Okay. So hence in the sufficient part, and this completes the proof. Hence the theorem. Okay. So this completes the theorem. So this is the sufficient part.